We move on to the next talk, which will be given by John Bozek from Synchrotron Soleil. And the title of this talk is Ultra-Fast X-ray Science with an X-ray split and delay device for the AMO instrument at LCLS. John.
Well, and I can start by introducing it. What I'm going to talk about is this X-ray split and delay device that we developed at LCLS, but in part we don't have enough results to make a full talk out of, but I also want to motivate the field a little bit by talking about how we can study molecular dynamics with X-rays in general. And we've heard some beautiful talks at this meeting so far about generating short pulses with lasers, either attoseconds or high harmonic generation, and you have this beautiful phase relationship between the attosecond pulse and the driving IR field and things. It can be hopefully similar with X-rays one day, and when Maria Manuel gave her presentation, I see, in the future that we have these beautiful sources that have phase relationships between the pulses. Right now, she didn't emphasize what the pulses look like. They're pretty hairy and pretty chaotic, and I'll give you a little view of that from the X-valve. So first of all, I'm going to start talking about some of the work that's been done at synchrotrons, and including recent work, and why it's still interesting, and then turn to FELs, and I'll very quickly go over the properties of SASE FEL, since that was so well introduced by Maria Manuel. So we have to go back, way back in time, to 1986 to get to what I consider the beginning of ultra-fast X-ray science. Looking in the audience, many of you weren't even born then, let alone doing science at that point. I was actually in my PhD then, so I can claim credit for being around when this happened. And Paul Moran and Ren Nenner decided to look at what happens in the electron spectrum of HBr when you excite it to this core state resonance. And this was driven by the fact that people had started to look at resonant Auger spectra in atoms, in krypton and in xenon, and observed some interesting phenomena. And they thought what would happen is when you populate this broad, diffuse band, that you're just going to see broad, diffuse electron peaks accompanying it. And instead, what they found was a sequence of very sharp lines, well, very sharp by the standards of 1986 synchrotrons, and they later, after puzzling over them, assigned them to atomic peaks in bromine. Actually, Paul, in a review article, tells a very nice story about how they actually identified these because they made this measurement one day and saw these peaks and had no idea what was going on. So they went home, they came back the next day and made the measurement again at the same photon energy, and all of the peaks except these ones had moved. And what had happened is the monochromator was unstable, so it just gave a different photon energy, but these peaks don't disperse with the photon energy, they're static, and that pointed them to the clue that these are actually atomic lines that are resulting from the dissociation of the molecule. And what they assigned in the paper is what happens is when you excite this bromine 3D electron into the antibonding orbital, of course the molecule dissociates, and as the molecule dissociates, a competing process of the Auger lifetime is going on, and the molecule is de-exciting. It's a statistical process, so some of them occur quickly and some of them occur later. The ones that occur later, after the molecule has evolved along these potential energy surfaces, give rise to the atomic lines. So it was a nice first example of atomic Auger spectra from molecules. And it's actually still, even HBr is still a current topic. Pascal Leblanc and his colleagues recently published a paper, and I know Pascal is here, looking at the lifetime of the atomic state in bromine. So with high-resolution spectroscopy at modern synchrotron sources, they can access the natural line width of this, and they came up with a line width of 91 and plus or minus 5 MeV, which corresponds to 43 to 48 femtoseconds. It's a very good measurement of the lifetime. It would be something that would be difficult to do with a laser, very easy to do in this case for this particular, you're going to have to imagine I'm pointing at it, state. So it's still an area, and you can see these are actually the same spectral region. Here's the X state of the molecule, and here are these two resolved X state bands. Here's the A state band, whereas it's not resolved in the original spectrum. So higher resolution is needed to do this, but that's readily available at third generation light sources to be able to accomplish this. One of the other original pieces in the ultra-fast association of molecules that was very interesting to me when it first came out and somewhat controversial was this idea of Doppler splitting in oxygen. And so what happened here is driven by the theory group of Ferenc Gelmukhanov and Hans Agren, the experimenters in Sweden, decided to measure the Auger decays of oxygen in the plane and out of the plane of polarization of the X-ray light, and they observed this Doppler splitting. When they measured in the plane of the polarization of the light, they see two peaks. When they measure perpendicular to the plane of polarization, they see this one broad peak. And what's going on here, of course, is very obvious in hindsight, is the molecule is dissociating, and as it dissociates, one of the atoms, so the controversy was about the core hole localization problem. We won't talk about that, but one of the atoms carries the core hole from the excitation in it. It then undergoes an Auger decay, and that electron gets Doppler shifted by the momentum of the atom as it's separating from the other atom. And so if you measure in the direction the atom is moving, it's either moving towards the detector, in which case it gets more energy, or it's moving away from the detector, in which case it gets less energy. And if you measure in this other direction, then you don't see that, of course, because it's smeared out. So it seems obvious to me now, but I remember when this first came out, it was confusing. This is something that's also been recently revisited, and Xiaojing presented this on Wednesday, a brief overview, but of course I wrote my talk before I realized he was going to, I actually didn't recognize his name in the program, that's embarrassing. Well, it said Liu, how many Lius are there? It's like Smith. So what we have here is a higher degree of complexity of that same experiment, and this was done at Soleil and Cataline Miron's group, where they looked at the Auger decay of oxygen excited to this core-excited sigma star state, so, and then looked at the Auger decay from that, and then they used a coincidence spectrometer so they could measure both the electron kinetic energy and the kinetic energy and directions of the ions. And with this, they can plot then, for example, the electron energy versus the ion energy. And they excited to different states, either the sigma star or a 4p Rydberg state, which is obviously non-dissociative. It's not perturbing the bound state of the molecule. And what they found is they see what they assign as a molecular band, this broad band of electrons versus ions, and then this little shoulder on it that they assign to an atomic peak. Whereas when they excite the oxygen 1s level to the 4p Rydberg, they don't see anything affiliated with this atomic peak. If you plot this in a different way, if you plot now the ion energy as a function of the angle between the ejection of the electron and the ion, it becomes very clear what's going on here. When you plot the ion energy as this function of this angle, what you see is a very clear distinction between this atomic peak line and this molecular band line. And you see the dispersion is faster in the atomic peak line as a function of angle than it is in the molecular band, whereas here you see nothing. And so what's going on here is when the molecule dissociates, one of the atoms goes one way and one of the atoms or the other atom goes the other way, and then you get an electron ejection. If the electron is ejected in the direction that the ion was traveling, it will get more energy, which means, so then you have to reverse it, because that's going to be a recoil energy for the ion. The ion is going to get less energy because it's going to recoil from the electron, and so it's going to have a decreased energy if they're traveling back to back. If, on the other hand, the electron is going the opposite direction, no, I've got to get this straight now. If the electron is going the same direction, or the opposite direction of the ion, it will give it a kick in the other direction and it will gain energy. In the case of the molecular band, the electron is ejected from the whole molecule as opposed to from the atom. And what I forgot to mention is what we're really measuring is the oxygen ions in coincidence with the electrons, not the molecular ions, but the atomic ions. And so the recoil energy of the electron is distributed over the mass of the whole molecule, not over the mass of the single atom. And so the dispersion is slower for the molecular band than it is for the atomic band. This becomes maybe clearer here with a little bit of a sketch, where you see what we're doing. We're taking the electron bunch, and we're exciting it up onto this dissociative core state. And the molecule, the electronic wave package that we've created on this core-excited state begins to evolve. If the Auger decay happens quickly, then the molecule is still bound, and we project down onto this also dissociative state, but with the electrons coming from the full molecule. In the case where the molecule begins to separate and the electron still hasn't been ejected until the atoms can be considered two counter-propagating atoms, depending on which side the electron is and which side the ion that it's coming from is, it will be ejected and you will get two peaks, these Doppler split peaks essentially, and you can see that in this line here. Now, when Xiaojing presented this, they talked about and presented this in the idea that it's really essentially a case of a split of a which-way problem. When you have the molecule, you have coherent emission from two sites and you can't tell where it came from. It comes from the molecule, it comes from one of the two atoms, and so you get an interference in the far field, whereas if the molecule is separated into the two atoms and you tag with the recoil energy which ion or which atom that the electron came from, then you're describing which pathway the electron is coming and the interference should collapse. And that's indeed what they saw, that when they look now at the electron kinetic energy as a function of this angle, you see nice interference patterns when you excite to a non-dissociative state, this 4p Rydberg state. You still see interferences when you're exciting this molecular state if you look at the molecular band, but if you select now electrons that are corresponding to the atomic band, then you see that the interferences have completely been quenched. So even with slow synchrotron radiation, you can do this ultra-fast dynamics and learn a lot about what's going on. But it's not the end-all and be-all in terms of ultra-fast dynamics, because a lot of systems don't do what you want them to do. And so you need this very big machine, in the case of what I'll present here, the LCLS, and here's the 100-meter undulator hall of the LCLS, in order to access the femtosecond timescales with X-rays that you're interested in. Marie-Emmanuelle Capri presented this, but I'll just go over it briefly, because for me, this is the equivalent of the high harmonic generation people talking about the three-step model where the electron goes out and swashes around and comes back. The same thing happens here. You start with an electron bunch. It has to be very short. It has to be very bright and very intense. You pass it through a long enough undulator. It begins to emit radiation just like an electron bunch in an undulator at a synchrotron. The radiation interacts back on the electron bunch, bunching the electrons at the wavelength of the radiation that's being emitted. They begin to radiate coherently, acting as a supermassive particle, and you get an n-squared amplification, and fully coherent in the transverse direction. The problem is the bunch is too long, and there's no longitudinal correlation in a SASI undulator, of course. We've heard can't remember at this meeting, but at the previous iSwamp meeting about the Fermi accelerator, which uses self-seeding, or uses a seeded bunch to give you a nice coherently, a longitudinally coherent bunch. With the SASI undulator, and I started working at LCLS before it began to laze, the good story was when I went to LCLS, I had people, including accelerator physicists, telling me I was crazy. I was throwing away my career because this thing was never going to work. But you know, the chance to work there at the beginning was too interesting to pass up. So I went there, and it does work, but it's very chaotic. This is a time trace as a function of shot over 2 picoseconds or 2.5 picoseconds for this full window. It's really just a transitory absorption in a system, and you can see how much the time jitters. It jitters spatially and in intensity or energy. We call it pulse energy usually, and you can see here the beam pulsing around. And then it jitters in photon energy, and this is a series of shots recorded with the spectrometer in the SXR hutch, showing you a variation of 1 to 2% in photon energy of the beam shot to shot. So it's not exactly as promised. But there's been many improvements and continue to be many improvements to make the beam more stable and to make it more usable and to characterize what's going on with it so that at least you can make usable measurements. I'll show you now some examples of how we knocked the timing down when we started the LCLS in 2009. One of the first experiments we did was a pump probe experiment. We had a laser upstairs in LCLS and transported it down to the hutch. And this laser is locked to the gun laser, which is 2 kilometers away, and 1 kilometer of warm linear accelerator modules away. So you can imagine the electron beam relative to the 2 laser beams is jittering considerably, and that's what we see. But we still managed to do pump probe experiments, and this was with Phil Buxbaum's group as one of the first users. And the first experiments that we did was looking at molecular alignment of nitrogen. So we would drive a molecular alignment of nitrogen with the laser and then come in with a time-delayed LCLS pulse and ionize the nitrogen gas that we'd align. And you can see the recurrences of the alignment of the nitrogen. And if you pick out a few of these slices, you can see some cases you see a sharp peak in the middle and just shoulders on the end. That's when the nitrogen is aligned perpendicular to the direction of the polarization of the FEL beam. And other times you see these sharp peaks on either side, and that's when the nitrogen molecules aligned along the direction, of the spectrometer, so that when we dissociate it, you get fast peaks and slow peaks. So you can see that this recurs quite nicely. But one of the best things we found from this is this sharp peak in the middle of this mass overcharge peak of 14, which corresponds to atomic nitrogen, or dicationic molecular nitrogen, and happens to be dicationic molecular nitrogen, is a signal that bleaches with time. So if you look at the intensity, relative intensity of that peak as a function of time, you see that it's some level if the laser arrives before the X-ray pulse, but then it decreases after the arrival of the X-ray pulse. So what it is, it's a persistent signal that you bleach with the laser beam, which is very important for finding T0. If you've ever done a time overlap experiment, if you're trying to find the overlap of two peaks in time and you have time and space and all of these things to consider, it can be almost impossible. But if you have something that turns off and on over T0, it becomes much easier to find the time. So this was a very important discovery. Then in order to stabilize the time measurements, we developed an optical laser X-ray cross-correlator, which was actually based on something that had been done on flash. And essentially, in this case, all of this red stuff is your laser beam going through your interaction region, and a part of it going to a silicon nitride thin film that's also being illuminated by the X-ray beam. And what you see is that the X-ray beam changes the optical properties of the silicon nitride film so that depending on the relative arrival time of the X-ray beam, you'll get a wave front or an intensity front that's changing the reflectivity of for the near IR radiation. And so depending on the position of this intensity front, it tells you about the timing of your relative pulses. And so with this, we can sort down to less than 50 femtoseconds of timing jitter instead of the sort of inherent 280 femtoseconds that has been observed. And it's since been improved using spectral instead of spatial encoding, so it becomes a little easier to use. And in some instances, we've been able to quote down to 10 femtoseconds with the operation of this. So with all that in place, now let's talk about a laser pump probe experiment. And this was one that Artem Rudenko did, looking at the dissociation of methyl iodide and wanting to ask the question, how do the electrons transfer from the methyl group to the iodine group after you separate it and then come in and ionize the iodine further. The iodine cross-section at 1500 eV is 60 times higher than that of the methyl group, so you'll selectively pump energy into the iodine atom or pump electrons out of it. And the idea here, and Robert Moshammer presented this in his presentation on Wednesday, talking about iodine, is that the molecule, when it's intact, the iodine, when it has a core hole on it, can draw electron density from the methyl group. But as the molecule begins to dissociate and begins to fall apart, eventually a barrier grows up between the two potential wells of the methyl group and the iodine group. And when the things move far enough apart that you no longer have access to the electron density on the methyl group, or the iodine no longer has access to the intensity or the electron density on the methyl group, and it's fully localized. So you can see this is a simple model for electron transfer mechanisms, which are very important in a lot of chemical problems. And all of these things are happening on the femtosecond timescale, so you need a free electron laser and an ultrafast laser to look at it. The ion spectrum is a very complex, ugly-looking thing for methyl iodide in this 1500 eV pulse after an 800 nanometer pulse. But if you look at it in a momentum-resolved spectrometer, it becomes quite beautiful, eerily beautiful, actually. So this is the different charge states of iodine, and you can see that their momenta or their kinetic energies are represented by the size of the circles around the central point. And let's focus in on this iodine 6+, mostly because it's a nicely isolated channel. We don't have to worry about overlap. And then look at the ion kinetic energy as a function of the delay time between the infrared pulse and the laser pulse. And you see three regions here. You see this diffuse band we'll call 1, and it appears only in the FEL data, or it appears in the FEL only data as well. It's just related to the Coulombic explosion of the molecule. The X-ray beam comes in and pumps electrons out of the iodine and out of the methyl group, and the Coulomb explode and give you about a 7 eV. I keep pointing at that screen. That doesn't help you, does it? A 7 eV band of ion kinetic energy. This other region here is a time-dependent curve that goes down from short time with high kinetic energy down to some asymptotic level at high delay times. Thanks. And you can see it's a time-dependent phenomena that's obviously related to some sort of Coulomb repulsion, where you initially separate the iodine in the methyl group with the laser and then come in later with the FEL pulse and charge up both the methyl group and the iodine, and depending on how far apart they are, they experience a Coulombic repulsion. But this third region here is an interesting one. It's a neutral fragment of methyl with an iodine, and the methyl has to remain neutral because there's no kinetic energy increase as a function of time. But what there is there's an intensity increase from 0. You can see there's no intensity at 0. It only turns on after some time. And this again, I think Robert showed something similar in I2, where you can look at the intensity of that peak as a function of delay time, and you can see that there's a threshold at which point it turns on. And that threshold is related to the fact that if the iodine has access to the electrons on the methyl, it will take them, they'll charge up the methyl group, and they'll coulombically repel. It's only when the methyl group gets far enough away from the iodine that it can no longer take electron density from the methyl group that you start to see this turn on, and you can see it changes as a function of the charge state. I'm talking too long, and I haven't even gotten to the X-ray split and delay, which was promised in the title. Here's our poor man's version of the X-ray split and delay. When we first started this project, we had the idea of building a proper 8-mirror X-ray split and delay so that you could cross through 0 time. But because of the short wavelength of the LCLS, even in this soft X-ray region of 280 to 1700 EV, the mirrors become very grazing incidents, and it would have been an 8-meter long or 6-meter long device and cost around $2 million, neither of which we had in our budget. So we decided to build this 2-mirror device, and with the help of Brendan Murphy and Nora Berra's group, we designed and built this device. It uses essentially a first mirror to intercept part of the beam and reflect it to the focal point or to the interaction region, and a second mirror which takes the rest of the beam and takes a different path to get there, so therefore a delayed path, and that path difference can be changed by moving and changing the tilt of the mirror. And then it had the challenge that it had to be inserted between the focusing optics and the instrument. This is a very technical drawing, but it's in this space, and pump probe experiments are inherently multiphoton, so you want to preserve as much intensity as you can, so that forced us to try and design a short device in this case to keep the focal length of the mirrors as short as possible in order to achieve the high intensity. And then in reality, this is what it looked like. We spent a lot of time worrying about edge polishing a mirror right up to the edge, and it turns out it was a trivial problem for Zeiss. So if you ever want an edge polished mirror, you just call up Zeiss and they make one for you. This is the edge itself, and you can see it's beautifully polished right up to the edge, and there's a few nicks, but nothing severe at the edge of the mirror. But so that was a wasted time. And then the rest of the devices had to be developed to be ultra high vacuum. It's right beside our focusing optics, and everything had to be the usual ultra high vacuum thing. Because of the nature of the device with this tilting and moving mirror, we spent a lot of time worrying about ensuring that we could overlap these beams in space with different time delays. So we spent a good portion of our commissioning time worrying about that, and in the end, we ended up imprinting the beams into I think this was lead tungstenate, so that you can see that we can very accurately control the positions of the two beams from the two mirrors, and when we think they're overlapped, they're actually overlapped in space. And then this one also shows you this X-ray laser cross correlator, but now with the two beams purposely separated, so you can see that their arrival times are different, so that we're really inducing, in this case, 150 femtosecond time delay. With my last 2 minutes, I'll talk about the actual experiment that we did in the last 2 minutes of the beam time when we realized that we were running out of time. And we again turned to methyl iodide, in this case at 1600 EV with 50 femtosecond pulses. And just with a normal time of flight ion spectrometer, we didn't have the time to put in this nice delay line anode so that we could see the momenta of the particles in this commissioning period. But what we did see is if we have the high charge states of iodine in methyl iodide, if we look with no delay between the two pulses, so all of the intensity is arriving within the pulse duration, within this 50 femtoseconds, then we saw a very flat peak profile for these iodine peaks. And if we increase the delay to 70, 150, up to 200 femtoseconds, you can see these peaks sharpen up considerably and increase in intensity in this region. And we ascribe this to the fact that when the pulse is all arriving at the same time, then you create these high charge states by photoionizing iodine in the molecule, and you create this Coulombic repulsion. It can take electron density from the methyl group, so you have a carbon 3+ repelling an iodine 15+ or something, and you create a Coulombic expulsion or repulsion, and you get very high kinetic energies. So you get very little iodine with low kinetic energy in that case. On the other hand, if you come in with a pulse after 200 femtoseconds, then the first pulse can dissociate the molecule. The methyl group can move far enough away that the iodine no longer has access to their electrons. And then the second pulse can highly charge the iodine atom and give rise to this low kinetic energy in this point. So you can see, obviously, that the type of results we had with Artem's beam time would be much nicer, but this was a commissioning time. There was a further experiment that was done by Phil Buxbaum's group looking at X-ray-induced isomerization in acetylene, and Phil's giving a plenary talk on Monday, and I'm hoping he's going to talk about that because this has just been accepted for publication in Nature Communications, so I didn't want to show you any of those results at this point. Marie-Emmanuelle Crupry talked about this slotted foil in order to generate short pulses. It can also be used to generate time delayed pulses. It looks something more like, I'm sorry, I keep pointing on that screen. It looks something more like you to get your fast food wrapped in than something you'd put in an accelerator, and yet it works very well. It goes in the bunch compressor, as she said, and it essentially creates time-separated pulses of electrons that will laze and then spoils the rest of the electron beam so that it won't laze. And people have used this for experiments to do multi-pulse experiments as well. So in conclusion, I wanted to show you that molecular dynamics with X-rays can be done at modern synchrotrons and FELs. The synchrotrons, you can use this ultra-fast dissociation. They have good resolution. We've got elegant tools at synchrotrons that have been developed by most of us in the room over the past 40 years, and frankly, easier access to beam time. If you've applied for beam time at LCLS, it's very difficult to get beam time. But we do apply for beam time there because the FELs give you this pump probe capability and true temporal resolution. When you saw the list of authors on these papers, you get this extraordinary effort from people coming in with different expertises to do these experiments, and it's quite wonderful. And frankly, the facilities are investing a lot of money in these tools to do these experiments because they've spent $1 billion on their accelerator. They want to make sure it's used properly. The future, well, you saw from Marie-Emmanuelle Crupry's talk that more FELs are coming online, shorter pulses, higher rep rates, improved characterization, and more lasers are being used at synchrotrons as well. Finally, in acknowledgements, there are several groups to acknowledge. My new team at Soleil, where I've taken over from Catalin Miron, so he's moved on to Eli. He saw the light of lasers. And my old team at LCLS, who helped with all of the experiments there, the X-ray split and delay team, including, or in particular, Brendan Murphy, who was the postdoc responsible for it, the LCLS users who gave me permission to show the results, and of course you for paying attention to me all this time. And just a little bit of advertising, there's 2 positions I have open with my group in France. One is a beamline scientist and another as a postdoc. We were encouraged to submit these postdoc possibilities to the conference, and we're going to be using the AtoLab attosecond lasers to do reaction dynamics, essentially electron dynamics in oriented molecules. So thank you very much.